All right, thank you very much. Today my talk will be on using GaN FETs for envelope tracking buck converters. I will start my talk first having a quick overview of what is envelope tracking. Then we'll look at why we would want to use GaN FETs for envelope tracking, and if we are to use them, how will we maximize the performance of the devices in circuit. We will then look at some experimental results that we've achieved with these devices, and finally we'll look at some of the limitations that's come out of the testing to show actually where we're heading and what do we need to do to progress further. We'll end it with a summary, and we'll have some time for some questions and answers. So let's first start with the overview for envelope tracking. So the mobile data traffic forecast for the next few years shows that there's a significant growth in the amount of data that will be transmitted. To keep pace with that, it will require an exponential growth in the data using modern modulation techniques such as 4G LTE, which requires an increase in the spectral efficiency and pack more data bits into each RF channel. However, the result is an increasingly complex waveform with an increasing peak to average power ratio expressed as PAPR. This increase in PAPR has had a serious impact on the efficiency of these RF amplifiers, which has actually gone down even with improved materials and technology. To explain why that is, consider this representative diagram showing a power amplifier efficiency on, versus output power, with output power on the x-axis and efficiency on the y. We can see that with a peak efficiency, it is possible to get as high as 65%. However, as you increase the PAPR, the average power output of the device is much lower than that of the peak, and efficiencies can be as low as 25% or even lower. And this variation in the output power is what generates the heat in the device and lowers the efficiency. But what if you can modulate the DC supply? If you were able to modulate the DC supply to follow the average output power, i.e. the envelope of the signal, you would be able to drive the RF amplifier back to an efficiency very close to its maximum efficiency, and thereby increasing the overall system efficiency to almost 50% and reduce the overall system losses down to a third of what it is currently. But to do that, you need to be able to have a bandwidth on this supply of 60 to 100 megahertz for 4G LTE as an example. So how is this done? Typically, it is not practical to achieve this kind of bandwidth with a simple switcher by itself. So hybrid implementations are typical. This would combine a very efficient switcher with a lower bandwidth with efficiencies well beyond 90%, and combine it with a linear stage that has the high bandwidth component but a very low efficiency. So to improve the overall system, the idea is to push the bandwidth of the very efficient switching converter and limit the total power and bandwidth required by the linear stage. So improving the switcher bandwidth and switching frequency improves the overall envelope tracking efficiency. It increases the switcher stage bandwidth, and it simplifies the linear stage design, or in the extreme case can remove it entirely. And finally, it increases the bandwidth of the overall system. Increased switcher will allow the linear stage to have the same ratio of minimum to maximum bandwidth, which will push out the overall bandwidth well beyond 1 megahertz. This will allow to have an amplifier with increased fidelity. So why would we use GaN FETs for envelope tracking? To first look at this, these kind of switching converters will be hard switching. If we look at an idealized switching waveform from at the turn on of a device, there are two intervals shown here. The first interval is in blue and the second one in red. During the blue interval, the current through the device rises well before the voltage across it decreases. During this interval, the power is dissipated in the switch, and the amount of time it takes for the current to commutate is related to the first charge term below QGS2. Conversely, in the second interval, the current is already flowing through the device, and now the voltage across the device decreases until it's fully on. During this time, the switching loss is dependent on the device term QGD, or millicapacitance of the device. Thus, we can see for an idealized switch, the amount of power loss that will be incurred during switching is proportional to the QGS2 and QGD terms. If we are to look at a hard switching figure of merit, which basically takes these two terms and adds them together and multiplies this by the RDS on, you will end up with a near constant term for a given MOSFET or GaN technology, and can be used to compare the performance in a hard switching application between MOSFETs and other field effect transistor devices. On this graph, we can see the figure of merit on the right-hand side and voltages from 25 to 250 volts. The blue line shown at the top shows a line approximating the best MOSFETs available today from various vendors. Lower figure of merit is better, as less charge will mean faster switching. On this line, we can see the dark green second generation EPC2 devices, as well as the latestly released Gen 4 devices, which shows even further increase in performance. Overall, these latest devices show about an 8x improvement over silicon at 200 volts, a 6x improvement at 100 volts, and at lower voltage a still exceptional 3.5x improvement. Another family of parts that are specifically made for high-frequency switching, as for envelope tracking, are shown here. We can see these devices are different from the previous ones in that their RDS-ons are in the range of 100 to 500 milliohm. Please note that all the charges shown here are actually in picocoulomb, not in nanocoulomb as is typical, and the devices have reverse capacitance values down in the hundreds of femtofarads. So these devices are made to be very small and be able to switch at very high frequency. So for these devices, how do they compare against similar high resistance MOSFETs? To do the comparison, we compared one of these generation 3 high resistance GaN FETs versus second generation low resistance 100 volt GaN FET, as well as equivalent packaged MOSFETs with similar unresistances. The only devices we could find effectively were the 30 volt BGA devices. And we can see here that the best in class 30 volt BGA MOSFET has a similar figure of merit to the second generation 100 volt pod, while the new third generation EPC 8005 has half the total QR product of the 30 volt pod, while being able to switch at double the voltage. Furthermore, having a good figure of merit isn't enough to make a good switching device at high frequency. Because of the high frequency and high switching, high DVDTs are unavoidable. A device with a high DVDT turn-on immunity is required. To achieve this, the QGS1 term must be much larger than the QGD of the device. The QGD is the plateau ratio, so it's a plateau charge as shown previously in the idealized hard switching diagram, while QGS1 is the charge subthreshold of the device. And we can see here that on the x-axis, the length of the QGD rectangle is much shorter than that of the QGS1. However, this defeated half rated voltage, in this case 20 volt or 40 volt device, but also all the way to rated voltage. And we can see here, if we extend this graph to 40 volt, that the VDT immunity still remains. So presented here, we showed that there is the GaN FETs offer a significant improvement in the device performance, both in the immunity and in hard switching of figure of merit, which conceptually will allow the devices to switch much faster than MOSFETs. However, parasitics in the devices such as common source inductance makes this less practical. So what is the impact of common source inductance? Firstly, by having common source inductance in the device, which is the inductance that is common to both the drain current loop and the gate current loop on the source side of the device, it generates, during switching, during the IDT event, it generates a voltage that opposes the gate supply and thus effectively reduces the amount of gate current that can be driven into the gate. This has the effect of lengthening the current commutation time and thereby significantly increasing switching losses. This effect of common source inductance has been well known in the industry with MOSFETs. And here we can see the evolution of some of the MOSFET packages to try and address common source inductance as well as other packaging related inductance parasitics. The initial SO8 MOSFET with its long skinny leads and having the device elevated above the PCB generated a significant amount of inductance, especially common source inductance. In the power loss diagram shown in the bottom corner, we can see that for a given device, for power loss given device, there is about 80% of the losses are induced by the package. If the device had no package, it would only have incurred the original 18% of power losses as shown at the bottom. With the introduction of the Aleph pack, the reduction of common source inductance was achieved by a copper strap and placed it to the PCB. The drain inductance as well was significantly induced by soldering the device directly to a copper lead frame that is soldered directly to the PCB. And in this case, the package-related losses are only 3/4 of the total losses, but still significant. The next package that came across was the direct FET. Understanding that common source inductance was the main contributing factor to switching loss, the device was turned over with the source of the device directly in contact with the PCB. This allowed a significant reduction in common source inductance. However, the drain on the back of the device still had to be brought down to the PCB through the metal can, which still added inductance. Even so, the package inductance-related losses were reduced to about half of the total losses. With an GaN FET's LGA land grid array structure, the drain source and gate terminals of the device are all on the same side of the die. This allows direct mounting of the device onto the PCB to minimize it bringing the drain from the back of the die down to the PCB. So there's no drain inductance compared to the direct FET. Furthermore, by interleaving the drain and source terminals, the inductance of the package can be further reduced. Here's a picture of what such a die actually looks like. So in this case, the total packaging related losses only form about 20% of the total device losses. The impact of this improvement in packaging related parasitics allows a smaller penalty in switching loss for a device and allows the device to switch at higher and higher frequency compared to the device with larger device parasitics. However, common source inductance isn't the only important parameter. we've already shown that common source inductance have a significant impact on the overall switching loss. And we can see from this graph that the losses will increase quickly with even a few hundred picohenry of common source inductance. However, the power loop inductance formed by the high-frequency decoupling cap and the two switching devices also have a large impact on the switching performance. It is not as detrimental as common source inductance, but it can significantly increase the switching losses even down below 1 nanohenry. If we now look at the EPC 8000 series package, if you look at the 8000 series package, we can see that unlike the Generation 2 device shown in the previous slide discussing inductances, we can see that the gate and gate return are running parallel to each other on the left-hand side of the device. Drain and source terminals are on the top and the bottom of the die and are located perpendicular to the gate and gate return. The structure has been designed not only to minimize the package inductance, but also the overall loop inductance and layout inductance on the PCB. To better understand how this works, let's consider two of these devices in series to form a buck converter or similar half-bridge switching topology. So here we have the top layer of the PCB with two devices shown facing up. If we remove the devices, we can see the gate terminations and the pinouts of the devices. We can see that for a half-bridge, the bus supply comes in at the drain of the top device, goes through the device to the source, down to the drain of the second device, and down to the source, and then to ground. We can see this power path current is orthogonal to the gate drive currents, which are coming in from the left into the gate and will return through the gates, a separate gate return path to minimize common source inductance. As stated, these are orthogonal to each other. Furthermore, to close these loops, there are a number of vias on the ground source return side and also on the gate return. By adding these vias on the subsequent layer underneath the second layer in the PCB, these currents can then be brought back to the gate and to the bus cap to have equal and opposite currents flowing in the top and second layers. These equal and opposite currents not only limit the inductance, however, they limit the inductance through cancellation of field by having the currents equal and opposite and having them coupled to each other on the two layers. This also limits the electromagnetic energy stored within the two layers. Further improvements are possible by bringing the first inner layer as close as possible to the top conductor. So to recap, the improvements that were made to the 8000 series device to especially work with high frequency applications is to reduce the active area to improve switching, minimize the hard switching figure of merit to further reduce the switching time, achieve complete the VDT immunity, as it would not be practical to have a gate drive close enough or with low enough impedance to hold the gate down. Separate out the gate and power loops to minimize common source inductance, and then minimize both the power loop and gate loop inductance separately through generating a pinout structure where these loops are orthogonal to each other and also allow the current to flow perpendicular to the pads, resulting in wide, short traces to minimize the overall PCB inductance. So with the analysis behind us, let's look at some experimental results. Here's an example of a demo board using the EPC 8000 series devices. And we can see the gate driver, two devices, and the high-frequency DC bus capacitance If we zoom in on the board on the right, we can see that the whole structure fits well within the SO8 footprint of a single 5x6 MOSFET device. Some experimental results. Here we can see the 8000 series device switching 20 volt at 10 megahertz and switching 4 amps with a rise time of around 500 picoseconds. The fall time is driven by the load current, and in this case the fall time is as low as 400 picoseconds. Of note is the fact that there are no measurable overshoot, even though a 1 gigahertz 100 to 1 transmission line probe was used on a 4 gigahertz scope. Furthermore, it is possible to achieve efficiencies of near 90% even with step-down ratios greater than 4 to 1 with an input voltage of 15 volts and switching at 3 megahertz. Here we can see the peak efficiency of around 89% and outputting 2 amps maximum. We can see that the overall power loss in light load is less than 200 milliwatts. If we push the voltage further, we can see the breakdown of the DIDT and the VDT intervals of the device. Again, as mentioned on the previous waveforms, there is no measurable overshoot. The DIDT interval can be seen here across the layout inductance of the device, as well as the separate VDT interval. During the VDT interval, the slew rate is as high as 75 volts per nanosecond. This results in a rise time of about 1 nanosecond and an overall switching time of just slightly more than that, switching 40 volts, 42 volts. If we look at the efficiency, we can see that at 40 volt to 20 volt, at about a 2 to 1 ratio at 10 megahertz, we are again able to achieve almost 90% efficiency. However, interestingly enough, the total power loss at light load is around 2 watts. If we now do a breakdown of the losses of the system, we can account for the conduction loss of the devices and inductor, the switching loss, the COSS output capacitance loss of the devices, and as well as the gate driver and magnetic core loss. And when we do this analysis, we can see that there's about a watt and a bit of losses that are not accounted for within the design. To understand where these additional losses are coming from, let's consider the current limitations of the system. So here we have a schematic diagram of 2 devices with a representative substructure of the level shifter gate drive that drives both devices. We can see that when you have a rising switch node edge, when the high side device is turning on, there is a capacitive current that flows through the bootstrap capacitor and charges up the internal IC well capacitance. This well capacitance manifests itself as parallel to the low side device and adds additional COSS losses. For these small high resistance devices, the well capacitance can actually be very significant. Furthermore, prior to the switching, the low side device will be on and the bootstrap diode will charge up the high side supply. At the start of the rising edge, the bootstrap diode needs to turn off and its recovery charge needs to be accounted for to have the diode turn off. To see the impact of both the diode reverse recovery and the well capacitance COSS, let's consider this no-load switching waveform. Here we are switching at 10 megahertz and the dead time has been significantly increased to increase the commutation interval. What can be seen here is that the rising and falling edges don't have the same slope, even though the peak and valley currents are symmetrical. Furthermore, there's an initial edge that is rising very slowly. If we calculate what the output capacitance, the COSS of the FETs are, the dotted line is what we would have expected the ZVS commutation to look like. And we can see there's a significant discrepancy between idealized and actual in-circuit performance. So what we can say from this is that on the falling edge, there are no diode reverse recovery. So the falling edge is purely COS dependent. From this, we know how much the devices are, and we can calculate how much the IC contributes to that. If we assume it is symmetrical, the same COSS will impact the rising edge as well. Any additional time that is taken on the rising edge is attributed to the diode reverse recovery. If we now calculate these quantities and calculate the losses associated with them, we can see that the bootstrap diode accounts for about half a watt of loss, whereas the COSS in the driver accounts for a similar amount. Furthermore, by adding these additional capacitance, the peak current during switching is increased, which further increases switching loss. From this, we can see that most of the unaccounted losses have now been accounted for, and from this we can also realize where is the limitation to the current technology to allow further improvements. From this we can see that if the GaN FET is paired with a better driver that with a significant reduction in both the driver well capacitance and the diode bootstrap diode reverse recovery losses, the efficiency can be significantly improved, with the light load losses halved and the full load efficiency improved by about 3%. So in summary, new devices enable higher switching frequencies. Switching at 42 volts at 40 watts at 10 megahertz is possible at 89% efficiency. However, the driver parasitics limit the actual performance of the device, and light load losses can actually be cut in half, and full load losses can be reduced by 25%. Thank you very much for your time.